Applying sensitivity analysis in real-time distributed system. When a system designer is required to design a real-time system, some challenges that he may face are tight completion deadlines and constantly changing system requirements. Additionally, all the performance data to perform testing analysis may not be available upfront, and the design would also have to take into consideration future possible modifications and upgrades. So how do we deal with design uncertainties while testing to meet specifications? We use something called sensitivity analysis. This allows the system designer to keep track of the flexibility of the system, as well as it assesses how individual hardware or software changes can affect the performance of the entire system. Here we have previous approaches to sensitivity and schedulability analysis and their limitations. We use in this analysis a software tool called SimTest. It was designed for performance analysis of heterogeneous systems on chips as well as distributed systems. It combines scheduling analysis for each component using event streams. During the analysis of the system, scheduling analysis for each component is performed and the results pass on to neighboring components. This is done until all the components are analyzed. In the analysis, we firstly wanted to find out the maximum that the execution time of any task in the system could be varied, and secondly, the minimum speed factor that the resource could operate at. Both these metrics had to be achieved without violating system constraints or schedulability. Remember, we want to focus on how varying one change in a component would affect the entire system. A binary search was used to determine the maximum value that a system parameter or component can be modified, but still lead to conforming system configuration. The worst case response time for any task in the system is determined by the execution time, the worst case execution time of that task, plus the sum of the worst case execution times of all the previous tasks. Since the worst case response time depends on the worst case execution time of that particular task, and all the tasks with priorities higher than it, then the response time, worst case response time, is monetarily increasing function of execution time. Maximum latency of a path is defined as the sum of the worst case response times of all the tasks along the path plus the buffering delay. Since path latency monetarily increases the core execution time of a specific task, then any latency value smaller than the maximum latency value will guarantee that the system conforms to the configuration. When we design the system, it could either end up in one out of two states. It will be a success if all the constraints are satisfied and all the tasks are schedulable. Otherwise, the system is in a failed state if at least one constraint is violated or at least one task is not schedulable. What is the exact value of a specific system parameter that represents the bound between success and failure? First, we use the algorithm for that parameter and then search using the binary search to get the exact value. The first algorithm is to calculate the task execution time variation. The system status, if it is a success, then the search interval is determined by the worst case execution time currently and the value corresponding to the maximum load allowed on the resource. The current load is determined by the sum of the ratios of the worst case execution time to the period for each of all of the tasks in the system. So if we vary the execution time of any particular task, then the new load on the system, or the new current load, would be less than the maximum load. So the execution time variation would be less than or equal to the period for the task that it is that we are varying, multiplied by the difference between the maximum load and the current load of the system. The second algorithm is to calculate how much we can vary the speed of a resource in the system. If we take the core execution times for each of the tasks that use a resource as inverse functions of the resource speed, then reducing the speed of the resource by a factor will increase the worst case execution time of the tasks that use it, as well as vice versa. So the current load, if it is modified by the factor, would be less than or equal to the maximum load. And so the speed factor we can determine is the ratio between the current load and the maximum load of the system. A hypothetical system was used to test the sensitivity analysis. It comprised of a microcontroller, digital system processor, dedicated hardware, all connected via a bus, and it had a timer and 3 sensors. Here we have the execution time bounds of the different tasks in the system, as well as the frequency of the input signals. This table shows the results of the various tasks, their corresponding core execution times, and the maximum value allowed for task execution times if only one task at a time is changed. This analysis was performed with a precision of 10 to the minus 2 and a maximum load of 98%. The bar chart shows that for the tasks that share the same resource, the darker regions of the bar diagrams, which represent the reserves corresponding to each task co-execution time, are about the same percentage of the current worst-case execution time values. This suggests that it is possible that clocking down the resource could scale those tasks' execution time by a common factor. This next set of experiments were performed to determine the minimum speed factor of a resource, conducted using a precision of 0.01 and a maximum load bound of 100%. The current speed values in column 2 show the speed at a factor of 1. The table shows that as both resources HW and M and the microcontroller are performing only one task, their speeds could be reduced. This third experiment analyzed how varying the algorithm precision as well as the maximum allowed load of the system affected the algorithm runtime. It can be observed that for maximum loads greater than and equal to 97%, especially at the higher precisions, greatly increase the runtime of the algorithm. Therefore, it is recommended that the system is run at a maximum of 95% no matter what precision is required. In conclusion, we see that sensitivity analysis using a binary search technique enables us to determine the system reserves, it describes the system flexibility during the design phase, and it guarantees the system satisfies its constraints. Therefore, it is a good technique for analysis of real-time systems.